Hello, everyone. Welcome to this last session of the day. Thank you so much for being here. And 4 quick introductions. Simon-Pierre, myself, Sergei. We work for Bethesda Game Studios. And we're here to try to provide some insights for the following question. How difficult, maybe easy, it is to build a procedural game using advanced visuals for mobile platforms in Unity. So our experience comes from working on and shipping the Elder Scrolls Blades that you can download and play for iOS and Android devices. So today, we'd like to focus specifically on 2 things: our custom lighting solutions that we've done, as well as to talk about some profiling optimization work we've done both for performance and for memory. So with that, please extend your welcome to Simon-Pierre.
Hi, everyone. I'm Simon-Pierre, programmer on Blades. And today I want to talk about a few, oh, my clicker is not working, OK. I want to talk about a few lighting features that we've developed for Blades' very special requirements. As Sergei mentioned, high visual quality was a big focus for Blades, but as well, we wanted to create 3D procedurally generated environments. And as you'll see, those 2 things often clashed with each other. But before we get into that, let's just go over the structure of our levels so that you can understand the problems that we faced. So this is an example of an editor's point of view of a level in Blades. Our levels are made of custom standalone building blocks that we call rooms. And these rooms are assembled procedurally at runtime by our custom level generator. The red lines that you see in these screenshots actually represent the connections between these rooms. So as you can see, we have rooms of different shapes and sizes, but they're all universal in the sense that they all connect together whatever the size of the actual room is. And another important detail to mention is that for this project, we support streaming. So to support having larger levels without taking too much memory, we stream in levels, we stream in rooms and attach them to our level as the player progresses to the dungeon. This is an example of a single room. Rooms are prefabs that contain every single asset that we need to place that room in a level. It contains art content, level design data like spawners for enemies and loot and a bunch of other things, gameplay data for collisions, and then also lighting. And lighting is what we'll focus on today. For this project, we use Unity's built-in render pipeline, mostly because the scriptable render pipeline was not in a fully developed state at that point in time. We use a modified version of Unity's standard PBR shader, and every single room is lit with a mix of real-time and baked lighting. We use real-time lighting because it looks really great with Unity's PBR shader, but it also allows us to do stuff like dynamic shadows in key areas like this window in this screenshot. We use baked lighting because it adds contribution from indirect lighting, and it adds a lot of depth to our scenes. For baked lighting, we use light maps and light probes. And they're also pretty cheap because they don't add up as an extra cost if you add more baked lights. So that's all great, but at this point, you might be thinking, how do you actually resolve having procedurally generated rooms or procedurally generated levels with light mapped content? How does that work? Well, in practice, it doesn't really. By default, you get this. And this is light map scenes. What you see here is a harsh cut caused by light maps when they're connected around a point where 2 rooms connect. So this problem happens because we bake lighting individually per room, which can cause dramatic differences in levels of brightness and even color depending on the room. We don't know at bake time which rooms will get connected together because that's done procedurally at runtime. So we kind of need a runtime solution for this problem. And this runtime solution is Lightmap Blending. The goal here is rather simple. What if we could just blend both sides, both light maps on each side of the connection together, so that at the connection, it's a perfect 50-50 blend, and then we fade out that blend based on distance. It would make that seam disappear. But to get that, we need a few things. We need a second light map for the other side, so each side needs the other side's light map to blend with it. And since that blending would need to be per pixel, we need, for each vertex, a blend factor that's based on how far that vertex is from the connection. And then we need a second UV to know where in the secondary light map should we sample for that vertex. Once we have that, we just sample both light maps and then blend the color based on the blending factor. So we built a quick prototype. And this is a quick setup we made where it's 2 completely baked rooms with a blue light on one room and then a red baked light on the other room. And then we just added a small shadow in the middle to test that specific case. With blending on, you get this. So the seam is completely gone. There's a nice purple in between the blue and red room. But that shadow is kind of weird. The problem here happens because we don't have enough information. We don't know what that blue room shadow should look like beyond the edge of that room. So what we end up doing is just extrapolating what's at the seam. So it might give some results like this where the data at the seam gets overrepresented. So we tried doing something else for this problem, which is creating a mesh that is exactly the shape of the connection, but stretched by a fixed distance. We made it so that this mesh gets light mapped in the editor when you bake the lighting of your scene, but it's never actually rendered in game. It's used exclusively for its light map data for blending. So that gives us a representation of what the baked lighting should look like beyond the edge of the room, which gives us better data or more accurate data to do an actual blending. So we built a second prototype out of this, and this is a very similar setup to what I showed before, and this is with blending on. We can see the seam is still gone, but the shadows kind of fade out in a more natural way. There's no more stretching needed because we actually know what those shadows should look like beyond the edge of the room. So let's leave the wonderful world of programmer art and actually show some in-game results. So this is the first screenshot I showed you, which is a completely unshippable result. And then with blending on, we get this. We went from something that's unshippable to something that no one will ever notice. So that's good, but what are the limitations of this system? Well, we end up having to do an extra texture sampling per pixel because we texture 2 light maps instead of 1 now. But we only do that on models that are actually near the connection. So it's not a huge cost. It's not something that showed up in profiling in any way. One of the big costs is actually calculating the secondary UV for each vertex of the models that we need to blend. This involves basically trying to find the closest triangle on the extension mesh for every vertex, and it can get mathematically complex. So what we ended up doing is just running that complete step in a background thread. Because of the way we stream in new rooms, they're always streamed in outside of the view of the player. So we never actually need to apply blending immediately. If it takes a second for Lightmap Blending to kick in, it's not a huge issue. And then finally, it's also incompatible with Unity's static batching because we end up modifying meshes at runtime, so it doesn't work if that mesh has been batched with something else. That's great. That fixed our main light map issue. But I mentioned earlier that we also use light probes. So as a quick primer, light probes are objects that contain directional lighting information for a specific point in space. It's a built-in feature in Unity, and Unity uses it to sample baked lighting at runtime for dynamic objects. So it's a complementary feature to lightmaps. Lightmaps are made to apply baked lighting to static objects, and light probes are made to apply baked lighting to dynamic objects. The problem that we have with this system is that it doesn't work with a procedural pipeline for two reasons. One, Unity saves the light probe data in scenes, and I mentioned earlier that we use prefabs. The second one is when Unity bakes light probes data, they're baked in world space in their original scene, and you can't actually move them. And because of the way we build levels, we always take a room and then place it at its proper place based on our procedural generation. So we need to move the position of probes. So that doesn't work for us. So this is a very simple representation of Unity's light probe pipeline. There's a first section that's light probe generation in the editor, where when you bake your scene, Unity generates light probe data for every light probe that you've put in your scene. And then at runtime, the Unity renderer actually samples that data for every dynamic object that you have in your scene. And then for every dynamic object, it'll figure out the closest probes to your object, interpolate their values, and then send that over to the shader. Then the shader will just render your object based on that information. So here, all of our issues are actually located in the middle section. So what if we just replaced it with something else? That's what we did. When we bake the lighting, we actually take the probes and serialize all of their data into a binary file that we attach to each room. And then when we spawn the rooms in our game, we actually load that data, and then we add them to a global level-wide network of probes that we can then sample for every object that we have, and then send that information to the shader. A quick problem that we had while trying to do this is Unity's format for when it exports data, when it generates data for every light probe, is that it generates a spherical harmonics L2 object instance for every probe. But the shader expects something different, but it wasn't clear for us what the format was. This is actually explained in a small blurb in the Unity documentation that references a paper by Peter Pike Sloan, and it mentions Appendix A10. And Appendix A10, if you actually look at that paper, contains the exact formulas that you need to transform a spherical harmonics L2 into the format that the shader expects. So it was our missing link in that system. So then, how do you actually pass that information to the shader? Usually in Unity, the standard way of doing this is to use a material to fill in the shader properties. But the materials in this case don't really work because we could have different data for every single dynamic object in our scene because it's in a different position in space, so light probe data will be different. So we don't want to create a unique material per object because that breaks Unity's batching, which will make rendering slower. There's actually a feature for this in Unity called material property blocks. It's a way to fill in shader properties for a specific renderer without having to go through a material. You just need to set those values on your renderer through the material property blocks API, and then add the per renderer data tag to your shader property, and then Unity will automatically link those two together and fill in those values for you. And you also need to, for every renderer, set the light probe usage value in the editor to custom provided. What that tells Unity is that you're now responsible for filling in those values. If you don't do that, Unity will just squash your value every frame. So some considerations for this. This system worked really well for us, but there are a few key details to mention. The process of sampling the network for every object can get pretty expensive if you have a lot of objects in your scene. But you should be careful about not sampling the network if you don't need to. So if a dynamic object hasn't moved since the last time you sampled the network, you don't need to do it again. Just leave the properties as they are. Same thing for static objects. Just do it once and then forget about them. Because of the way we actually fill in probes in our scenes, we fill probes through a 3D grid. So it's a completely regular setup, which means it kind of simplified the problem of finding the closest probes to any point in space, because it's just, we find the cell in that grid and then find the 8 closest probes, which are cube-shaped, and then we do trilinear interpolation to find a proper value for a specific position. But then, if you don't have a regular layout, that's a much more complex problem. Unity's system actually handles that, but we didn't have to re-implement something as complex. One last thing is that the ambient value of your scene is actually, the ambient color is actually set through the same shader properties as the light probes data. So if you don't add it to your light probes data, you'll basically squash and not have any ambient. So you're responsible for adding that data to your light probes data on your own. So with that said, I'll leave it over to Sergei, who will go over some performance and memory optimizations that we've done for the project. Thank you.
So there comes a time on any project where suddenly the team wakes up to the fact that the game doesn't run particularly fast on the target hardware. So anyone experienced that? I'm just kidding. You don't have to show hands. So if that happens, what do we do exactly? So Unity CPU frame profiler is obviously a good place to start. One would have to figure out, are we GPU bound or are we CPU bound? Let's say in our case, it is on the CPU side where we're facing issues. So what exactly do we see here? So in all honesty, this is not what we started with. This is past some number of optimizations, particularly for behavior side of things. But one thing that cannot be kind of escaped from seeing here is that the fact that rendering really takes a lot of cycles. So both on the main thread, on GFX device thread, there's a lot of cycles that are spent essentially preparing different draw calls and creating render batches to be sent over to the graphics device. So there's other things that can be seen that are kind of cool. Skinning and particle simulations are well parallelized, and on the worker threads you can see kind of those things being executed. But at the same time, all the good work that is going into ECS and dots, we really hope that the actual render is going to benefit from that as well. At the moment, it doesn't seem to be the case yet. So what are the main performance drivers for the CPU side rendering? Well, there's a couple. Ultimately, it depends on the number of draw calls that we're doing. And draw calls themselves, it also depend on number of rendering passes that we do. If we do a depth pass, if we do a shadow pass, if we have per pixel lights, there's going to be more draw calls sent over to the graphics driver. So we obviously need to control for that. In addition to that, what helps a lot, what is one of the major optimizations, is the efficiency of batching. As Simon-Pierre was saying, in our case, we have some problems or limitations for what we do, and batching is affected. Ultimately, also, performance depends on the efficiency of the graphics API as well. So we'll come to that. So ours is a procedural game. We have lots of rooms that we're drawing when the player is inside our dungeons. So one of the important things that we do in order to reduce the number of draw calls is visibility culling. So dynamic visibility culling is the path that we're pursuing because we cannot really pre-compute anything ahead of time. So we have dungeon levels in our game and also kind of more exterior forest-like levels. We do pursue different strategy for culling, for visibility culling in those two situations. For dungeons, we do sort of a portal-to-portal visibility calculation where we try to figure out if a given room can be seen through kind of a chain of portals leading toward the player camera. If that's not the case, we're going to eliminate that entire room with all the mesh renders that it contains. At the same time, we cannot quite do it in exterior levels because, like, you can see way more. But in those situations, we would go with essentially distance-based culling strategy. There's also another thing that we do in the case of our town level. So in a town, we have basically lots of buildings, and those buildings, they would obscure one another. Especially in a situation when a player camera is close to one particular building, there's lots of things that can be obscured. And so we ended up implementing a fairly simple dynamic occlusion culling system where we would select a particular building that is close to the camera. We'll figure out, based on its oriented bounding box, what is the kind of visibility frustum. And for the objects that are entirely within that visibility frustum, we're going to eliminate them and kind of not draw them. So all of that reduces the number of draw calls, sometimes quite substantially, and helps us kind of reduce the time that it's taking to drive the rendering on the CPU side. So one other thing that we must consider, specifically for Android side of things, is OpenGL versus Vulkan. So as you probably know, Vulkan is a more modern API. It is somewhat similar in its structure to Metal. It kind of processes state in a way more efficient manner than OpenGL. So it seems like a no-brainer, and we should kind of just convert over to Vulkan and see what happens. Well, we like to test things, so we did that. And so this is an example of testing a number of different Android devices, kind of running OpenGL and running Vulkan. And so we looked at a couple of things. One, what is the performance during loading? And also, what is the performance of the actual frame time? And unfortunately, the situation is not tremendously clear. So we noticed that for some devices, there's the shader caching that is done, and it's not super efficient. And every time the game is launching, basically, the shaders are getting recompiled. When you switch to Vulkan, that is not the case anymore. So this is great. But unfortunately, for other devices, when you switch over to Vulkan, the frame time suffers a bit. So is there really a way for us to try to sort of enjoy both sides of that? So we had a conversation with our partners at Unity, and one thing that they suggested and we ended up implementing is trying to do dynamic graphics API selection on launch. So the way it works is that we had to build a custom player activity in Java, and that is the one that actually receives all the kind of callbacks when the game starts, and it'll forward it over to Unity's own player activity. But what we can do when we receive control, we can verify what kind of device that is, and if that is within our list where we'd like, instead of, let's say, Vulkan to run it OpenGL, we would pass over a command line argument so that when Unity player initializes, it'll initialize with that specific graphics API. So we actually shipped it on a custom build, but this is one of the features, I'm looking at Christian now, that actually makes it into the main line. So I think more people can use it. Now, in all honesty, this is something that probably would not be necessary once all the device drivers evolve, and we probably would reach fairly soon the point where Vulkan is more efficient across the board. What we would suggest is obviously that you test your specific game on a range of devices, and if you can objectively measure performance and can benefit from running with different graphics API on different devices, this is the way to kind of take advantage of better performance for both. So to summarize quickly, we found that Vulkan is definitely viable. We didn't see a tremendous number of graphics artifacts when we switched over to that. And once again, test your performance on a range of devices. There are lots of complexity within Unity's rendering, lots of complexity within the graphics drivers. GPUs are not the same. So there's surprises certainly to be found. And if there's measurable performance gains, definitely consider doing sort of graphics API selection on launch. So this next thing is not a huge optimization, but we felt something worthwhile to maybe quickly talk about. So when the game starts, specifically, once again, on Android device, you can be running with quite a few different threads. Like there could be in excess of 40 threads that are running. There's a couple that are more important than others. Obviously, there's Unity main, where all the kind of the main thread, where all the behaviors are being run and so on. There's a Unity GFX device. If you're doing multi-threaded rendering, that's you will see it there. And obviously, there's a number of worker threads. So how exactly do those map onto actual device cores? So a typical Android device these days will probably look something like that. There'll be two clusters, a big cluster where cores are faster, they're clocked to a higher rate, and there's a small cluster which are more power efficient, but they're somewhat slower. So how does those threads map onto cores? So the way to check it out is obviously to try to run a systrace. If we do it, there's a couple of things that we can notice. So one is here. So Unity main jumps cores. It is not assigned to any specific core. And when within the same frame, it goes from one core to another core, that is fairly costly. Not only the cache is getting invalidated, there's like the whole state switch that is happening, so that's expensive. The second thing is the workers are actually on a big cluster as well. So they contend with both Unity main and with GFX device. So GFX device, you cannot see it here, but actually jumps cores as well. So what is happening on a little cluster? Well, not a whole lot. All right, so the default Affinity model that Unity uses for like those 8 core setups, and once again, you may have a device that have more like 10 cores or 4 cores, but most commonly you have 8. So that's the model. Essentially, everything is running on a big cluster. In all honesty, for a lot of situations, it does make sense because there could be other processes that are executing on a device, and also workers are not tremendously occupied. So they're enjoying faster clock rate, and the fact that they contend with the Unity main may not be that big of a deal. So, but once again, we like to try things, so we tried a different Affinity model. So we had quite a few fruitful conversations both with Unity and with Google, and thank you for those. What we've tried is basically to assign Unity main to a specific core, assign Unity GFX device to another core, and then distribute workers to other cores. So if we run a systrace, this is what you can see. You can see that Unity main kind of sticks to one, and then same goes for the GFX device, and then workers are kind of also spread. Now, one thing that is not there is what exactly is happening here. Well, the interesting fact is that Unity today would allocate as many workers as there are big cores. So we actually have a bit of a conversation going about that. Maybe we'll have a bit of customization and would be able to allocate more. We did find a number of use cases where we would have benefited from having extra cores. Like for instance, when we have to recompute the navigation mesh, this is taking heavy advantage of workers, and that is spread across multiple frames. So in that situation, having extra workers definitely helps. So to summarize quickly, Unity prefers big cores on Android devices. That may or may not be beneficial in all scenarios. So you can write a fairly simple native plugin and basically reassign, like discover mapping from thread names to thread IDs and reassign affinities to a different mask. That is fairly simple. And I wouldn't expect a huge performance gain out of that, but it's certainly measurable. In our specific case, we're gaining maybe about 5–7% of performance gain on the CPU side by reassigning affinities. So there comes a point on any project where suddenly we run out of memory. So if that is to happen, what do we do? Well, we have a number of different tools. And more often than not, we, in mobile space, run out of memory on iOS devices. Android devices these days would usually come with at least 4 gig of memory, whereas there is still a bunch of fairly fast iOS devices that have way less than that. So on iOS, if we run out of memory, there's a bunch of tools available. So we can run that and check what is going on. So if you try to do that, at least we did, and that's what we discovered, is that all of those tools give a fairly different reading. So if we run it and check what's happening on the Xcode widget, it shows that we're using about 1.18 gig of memory. If we check out Unity's simple memory profiler, it reports only 450 meg of memory. If we summarize everything that is reported by the detail Unity memory profiler, this is more than that, about 560 meg of memory. Like Instruments is sort of an ultimate tool in many ways, but it also, there's like a large discrepancy. So that is not tiny. That is not like 5–10% off. This is quite substantially off. So just out of curiosity, anyone encountered something like that? Dealt with that? Yeah, well, there's some hands. OK, all right. So what is going on? I'll try to go over that. Again, it's a little bit of a high-level view. It's a little bit more complicated in practice, but this is what is going on. So our game, there's at least 2 large memory allocators in there. So there is the native memory, where essentially content of the assets is stored, like texture data, mesh data, and so on. And there is a managed heap. So the managed heap is basically where all the C# objects are allocating from, right? And that operates within the large 64-bit space of the virtual machine. So obviously, that space is much bigger, much wider than the physical memory, right? But a lot of those pages within the virtual memory, they're not mapped to anything, so they don't have the actual backing. So within that virtual memory space, there is the device resident memory. This is actually something with physical backing. But there are several different categories of memory within that. So there is reusable memory, external memory, and internal memory. So external memory is what iOS using to store de-encrypted and decompressed pages of code. And reusable memory is what the graphics driver is using kind of for its temporary allocations. And finally, internal memory is what is used by everything else. So our game, both the native memory and managed memory, would be taking some number of pages out of internal memory. So there's more going on, though. So some clean pages can be unloaded. If certain pages have not been accessed for some time, they'll be unloaded. So what's the difference between clean memory and dirty memory? So clean memory is the one that can be reconstructed by reading it from somewhere else. So if you have some read-only statics in some library, or if you have memory mapped file that is read-only, that could be unloaded. At the same time, iOS also doesn't swap pages to secondary storage. It's not set up this way. But what it does do is it can compress some pages. If certain pages of dirty memory have not been accessed in a while, it can take those pages, allocate new pages actually for that, and compress data. And basically, if there's a page fault, something is trying to access compressed pages in the future, then the decompression will be happening. So this is what's going on. There's like a number of different memory types and different tools. They account sometimes conservatively and sometimes aggressively for the kind of memory taking within different types. So lots of tools would not, for instance, consider what is happening with memory compression. Some tools would not consider reusable and external memory. So what can be done, and kind of stepping back a little bit, the important thing for us ultimately is what Xcode widget is showing, because that corresponds to the value that iOS would be using to figure out when to jettison the app out of memory, right? So what we have done is basically we use the iOS functionality, actually Mac functionality, to grab information from the operating system, what is the current state of memory. It actually contains also the sort of the watermark, high watermark and the low watermark for memory usage. So we grab this data periodically, specifically during the loading of the game, and sort of create like a big matrix of numbers. It's like the way we use it would usually have a timestamp and also a name of a function where the reading was taken. And this basically contains all the data, what is happening with device memory, resident memory, reusable memory, external, internal. It also contains the reading from the heap, how much is allocated, how much is free, how much is used, and also we can track when exactly memory compression is happening. So memory compression is something to be careful with. We don't really have much control over it, so it happens when it happens. But unfortunately, because it needs to allocate extra pages, you might have actually a local spike in memory usage when compression kicks in. At least it's important to kind of keep an eye, is it happening a lot or not? So to summarize quickly, different tools account differently for those subtypes of memory for their reporting. Xcode widget is the one that is the most relevant. So the memory system, memory organization for iOS is pretty complex, and there are different memory types and different algorithms in play. And you can use Mac functionality to basically get a pretty accurate reading, and by combining like resident memory and external memory, that is very close to Xcode widget reading. So at least you get an accurate idea of what is going on. So coming back to the wall of numbers, one other thing that, again, not like a bit of a hacky little thing that we wanted to talk about is the following one. So the managed heap is implemented using the BOM garbage collector. So this is something that is open source. You can go and grab it from GitHub. Probably Unity uses something that is somewhat modified, but at the same time, a lot of the map file seems to match fairly closely. So there are a couple of things to check out here. Like one is whenever we try to allocate out of managed heap and it doesn't have enough storage, it expands. So sometimes, oftentimes, it may expand beyond what is necessary at the moment. So in that case, it grew, but then there is like 34 meg of memory that is really not needed for quite a while, right? And sometimes we end up with over 100 meg of free space within the heap. So this is not great, obviously, and heap, unfortunately, doesn't shrink super well. It does remap pages internally, that is happening, but it doesn't really shrink. If it expanded, it'll stay like that. So there's this one thing that can be done for that is to try to control that gross increment. And if you take a look at the actual code of the garbage collector, there's a particular point that makes a decision when to garbage collect versus grow the heap. And there's one specific global in there, GC free space divisor, that you can, once again, write a native plugin and sort of extern and modify. And that is the one that is sort of determines like by how much the heap would expand. So default value of that is a 3, meaning that the heap will be expanding by about 33%. So in some very specific situations, we kind of played with it a little bit and modified it with a different value. So you can try it with 16, so the heap will be growing much, much less. It is a bit hacky, and something to be aware is that this is a trade-off between running a garbage collector versus expanding the heap. So you may not be expanding the heap as much, but the garbage collector cost and performance cost will suffer. So when we were kind of closer to the end of the game, obviously the game is procedural. We're loading a lot of prefabs. We're unloading a bunch of prefabs. So we certainly run into situations with memory leaks. And it is through a detailed memory profiler, tracking leaks in a complex situation is fairly complicated. And the specific memory profiler, like the one that comes from a package, wasn't in super good shape at the moment. So we ended up looking at that, which is the low-level memory API that we have access to. So the API basically enables you to get a memory snapshot, and it captures everything. It captures the state of the native memory. It captures the state of the managed memory. And it provides connections. It provides typing information. And you can sort of grab it and kind of traverse it, collect data that is needed, and also collect it at multiple points and do a memory diff. So we ended up building a custom tool that enabled us to do exactly that, do a memory diff between two situations, and it'll show us for specific types how many objects have been added, what is the total size of this growth, and specifically for leak detection, what was helpful for us is to be able to see how many references to a given type are coming from other types. So in this case, there's something here with the picture image, we can put it there, and it'll show us that there are 4 references from some twinning class. So maybe that twinning class is running, was never freed, and that's a reason why this is leaking. So certainly an API that is worthwhile to look into. It's not documented super well, but the actual code for the memory profiler, it's in C#, so you can use that as documentation also. So to summarize quickly, garbage collection can be tweaked a little bit by external some of the globals and modifying them. It is a bit hacky, so it comes with the usual warnings. And C# objects themselves, outside of game objects and other things, they could contribute significantly in terms of memory. Different strings, different other like small types that may not be accounted in detailed Unity memory view may still be taking quite a bit of memory. And ultimately, low-level memory API enables to build custom tools for very specific different purposes, and that certainly helps specifically for leak detection. So with that, last but not least, thank you to our awesome team, both in Montreal, Rockville, Dallas. Some guys are here, Akram, Vincent, and Max, and Jibril. And Dallas, Mike is there. Thank you to Unity, Christian, thank you for your support. And thank you all for staying till so late today and listening. Hopefully that was useful.